I've been doing some projects lately that require little motors. This is a DC motor from an RC car. This particular one's 55 turns, which is a lot of turns, but it's what I have at the moment. And I've been having trouble, in part because I don't have a good understanding of their performance. You can get by with trial and error, which is what I've done so far on the pendulum projects, for example. I just crank up the signal into the controller if I want more speed. But that gets more and more difficult, and when you start trying to use more advanced control strategies, you have to break out forces individually for the motor and friction and other things, and when you start having to guess, things fall apart. The path to success just becomes much, much harder. So what we want to do is measure how much torque does this motor produce while under load from a full stop, completely stationary, up through a given number of RPMs, which I haven't determined quite yet. But how are we gonna do that? What we need to be able to do is to compare the energy between two states from the motor. So the easiest way to do that would be to store that energy up in something, and since the motor rotates, we can use it to spin something up. I thought first about winding up a string on a shaft, but this has a couple problems. It has a fixed distance from its lower position to the higher one, and then you have to wind and unwind the string every time you want to do it. If you don't hold it when it gets to the top, it'll fall. There's just some practical issues there. So then I thought about flywheels. The main thing that we're interested in here for the flywheel is the moment of inertia. And for a given amount of energy, a flywheel with a large moment of inertia, like this one, can spin slowly, whereas a flywheel with a small moment of inertia, generally a smaller one, must spin faster. And the moment of inertia equation for a cylinder of uniform distribution, i.e. something that's not like a pipe where it's all at the outside. So for a uniform distribution is 1/2 times the mass times the radius squared, as you can see in this diagram. A bicycle tire might seem like a great option because it has most of the mass on the outside, but it has a couple problems. First, I don't want to take my bike apart because I want to be able to use it. But more importantly, it has a lot of air resistance with the spokes and then the treads on the outer part. So something with less air resistance would be better because we know that any change in speed, up or down, down basically, anyway, comes from the motor. The air resistance is not going to speed it up. Anyway, I looked around and found the largest, heaviest cylinder in the garage. You might recognize it from a few past projects, like the counterweight desk and the cradle one, but we're going to use it here to try and make a flywheel. At first glance, the iron block looks pretty round. Everything seemed to be in order. I gave it a test roll. So I thought what I would do is to chuck it up in the lathe and drill a hole down the center, or at least center up that hole that's in it. So I changed to having the outside gripping jaws on there, but it became apparent immediately that it was not even close to being able to hold this piece. So what I did instead was to measure this block and determine that that center hole, or at least the start of a hole, it doesn't go all the way through, is pretty close to the center in all the different directions. So I'm going to drill that all the way through, run a shaft through it, and then chuck up that shaft in the lathe, and that'll let me turn down the entire assembly. I should probably invest in a set of reamers because I've had this experience more than once where I drill all the way through with the given size of a drill bit, which is a 1/2 inch in this case, and I have a 1/2 inch shaft and it'll fit great in part of it, and it will not fit through the center. You can see here there's a zone in the middle where it's not going to work. It was pretty close though, so what I did was to chuck up that shaft and I started turning it down. On the very end, I'm going to have an encoder, which is what you see there. This is a different encoder. It's a magnetic one. It's an absolute position one. I was pretty psyched that I got this. I've been wanting to try one out. It also has a serial output, so it requires a lot less wires and other hardware. So anyway, I turned that down for that, and then further up the shaft, I turned it down for one of my skateboard bearings. I got out my old RC10 GT nitro-powered RC car because I need a way to drive this shaft from the motor that I'm going to attach, and I need to be able to decouple it a bit so the vibrations don't go between them and cause a problem in friction. So what I'm doing here is I'm going to pull the CVD, a constant velocity drive joint, out of this car, and I used to have specialty tools for pulling these wheels off, but who knows where they are. So we get that all taken apart, pop that off of there, get the drive pin out, and we have our CVD. Now we need to be able to attach that CVD to the end of this shaft. So on the one end we have what we turned before, there's a little dimple in the center so I can put the live center in there. And then on this side I have the CVD. And what we're going to do is to drill a small hole quite a ways in, which is going to allow that center, that smaller part to go in. Well, here's the smaller one. And then the larger one, not quite as far. And we're going to tap the smaller one down in there. So we'll be able to push it in there, thread it in, and it'll lock itself into place. Now that the shaft is ready, we can do a quick mock-up, get everything on there, the bearings, the encoder, thread the CVD into the end, and it all seems to be in order. So we're ready to go ahead and drive this shaft through the center of the mass. I could probably just solder this weight onto there or tack weld it or do a number of things like that, but I prefer to have it the ability to take it apart. So what I thought I would do is heat it up and try and do a press fit or a heat fit, whatever you call it. So you can see it was about 55 degrees Fahrenheit, which is ambient, it's air temperature. You can see some ripples in the image here, which I didn't have a lot else to look at when I was heating it up, which took a bit, so I was watching that. But we got it heated up, and we eventually got this thing pretty warm. I think it was about 180 or 190 degrees total, and we're ready to try and drive that shaft in. As you can see, I overestimated the precision of my drilling, and that thing absolutely would not go in there, so I drove it back out the other side. Fortunately, I was fairly careful and the shaft wasn't damaged, so what I decided to do was to just ream this thing out until the shaft would go through it, and I turned down the shaft ever so slightly, partly to make it smaller and also partly to roughen it up. I had some unused epoxy laying around, which happened to be the quickset stuff, so I broke that out, and I was going to use that to glue it on there, but it's only good, it won't cure above 120 degrees Fahrenheit, which we just spent a bunch of time heating it up. So we dropped this thing in the snow and let it melt its way down to bring the temperature back down, and then we filled it up with some epoxy in there, spread some on the shaft, and pushed the thing through, twisted it around to make sure it was all mixed up good, and let it cure for a couple hours. After everything had cured, I went ahead and chucked this thing up in the lathe very carefully. Remember, this thing weighs about 22 pounds or 10 kilos. So I put that in there, and I had my live center set up on the tailstock, and I brought that in, which I had made the dimple before that I mentioned, and got that all set up and gave it a test spin. You can see that while it rolled pretty well on the table, it is definitely not round here, at least by machining, on a machining scale. And it's about as large as it'll go. I mean, there's very little room left at the bottom. Cutting this took quite a bit of time because I had to go slow because I couldn't rotate the thing fast, otherwise it would shake the whole lathe around quite a bit. And I couldn't take a particularly deep cut because it's not a very big lathe and this is a large piece. So I didn't want to just the motor. It didn't seem to like taking deeper cuts. So we just took our time and we took a couple hours worth of nice shallow cuts. So here we are after the first pass, the second pass, the third pass, and the fourth or fifth pass. And finally, after we've got the entire outside looking good, and you can see that we've got a pretty good pile of chips. Cutting down the side was interesting because when you go from the outside to the inside, there's a very big difference in speed where the cutter is contacting the piece. But every once in a while, like this particular cut, I hit the settings just right, and you can just sit here and listen to it hiss and make beautiful chips. The cutting fluid may not look like it does a lot of good, only coming in periodically, but I could tell the difference. My hand is not far behind this because I'm cranking it in, and I could tell the difference on my hand of the temperature of the chips hitting it. and also you occasionally see some steam coming off. So it seemed like a good idea, and just in general when I'm cutting, it seemed to cut a little smoother and quieter, so I kept giving it a few squirts every now and then. The other face was definitely not straight, but it was straighter than the other side, so I was able to clean it up much quicker. With all the faces complete, I chamfered the edges, and particularly that spot where there's a difference in diameter. And I spent a little bit of effort trying to polish it up, but that's not really my thing, and it didn't seem to help that much, so I just left it alone. I wanted to see the thing spin after all this work, so I put it on some bearings, set it on a couple 2x4s, and just spun it up by hand. I mean, it's nothing is holding it there, it's just the weight of it has dented slightly into the wood. And the thing kept spinning and spinning and spinning, and 5 minutes later it was still spinning. So I feel pretty good about it. It definitely seems to be doing its job. For the actual contraption, I set it up on a nice piece of roughly 1 inch thick cherry board, and mounted the bearings with the 7/8 Forstner and all the way through, so we can get our encoders and things in there. And everything looks good to go. I spun it up with a drill, and there is quite a bit of energy in this thing. The CVD to shaft connection has already been taken care of, but we need to hook that motor up to the CVD. So I took another piece of that 1/2 inch shafting, and I drilled it out down the center on both sides for the appropriate diameters, and we're going to use that with some set screws to get these connected together. Holding something small and round like this, still enough to drill perpendicularly through it on the drill press, is a lost cause, so I drilled out with a Forstner bit pretty close to the edge there and use that to hold it instead. And then I can center drill it and then regular drill it and run a tap down through the center, and now we're ready to go for our set screws. I used a 9-volt battery to do a quick start test on this thing just to see it rotate, and you can see that it's wobbling a bit because that coupler is too short. It's not perfectly lined up, and just causing a problem. So I made a longer one, and hopefully this will reduce that wobbling. It's not totally gone, but it's better, and I think I'll just have to live with it for now. So I mounted the motor up in a not particularly elegant fashion, but it does work on a piece like this. And what I really want to do is to keep the motor from rotating. I don't really care if it wobbles around a bit, so I'm just going to leave it like this for now. What I don't want to do is have I don't want to have friction in the shaft from constraining the motor too much, causing a problem on my measurements. And then on the other hand here, we just did a quick slip fit. There's an E-clip also, but on this magnetic encoder in that black potted area in the center is what actually measures it. That magnetic encoder is an absolute position encoder, which is actually not that good for this situation, which is kind of ironic because now I have the opposite of what I need again. So I pilfered an incremental one off the other project, and we're going to use that instead. To get useful information out of this, I need to know the moment of inertia of this cylinder, so I need to know the mass also. So it's going to overload the scale if I do it regularly. So I balanced it up like this, spun it around, and got 9160 grams total. And when you break it out into 3 different areas, we have the shaft, the main cylinder, and the cylinder that's slightly smaller than that, and you calculate the total moment of inertia, you get 0.0176. Now that number is useful because we know that the torque is equal to that moment of inertia times the angular acceleration. So we're going to drop that number in there, and then we have an easy way to take our acceleration, which was going to be in radians per second squared, and we'll be able to calculate the torque. Since I'd already used these rotary encoders before, I had some code and the wiring and stuff set up pretty well all ready to use those, and it only took a few minutes to get it going, which was really nice. But the problem is that I kept having these weird spikes, which you can see on the graph here, and I cannot for the life of me figure out where these are coming from. I tried everything. I tried different sampling intervals. I tried checking the loop time that the Arduino was doing, which came out perfectly even every single time. I tried a new decoder chip. I tried putting pull-down resistors on every wire, even though they weren't necessary before. And I am basically baffled. I just do not know where these are coming from. The electronic part is operating exactly the same as I was using it in the other projects, and it worked fine there. I had none of these problems. So in any case, I finally had to just sort of go with it since it seems to work fine 99% of the time, and I'll just smooth out the data manually. Just to be clear, I'm going to come back and sort out this problem, but for the moment I'm going to leave it alone and sort it out manually. So we got everything set up for the test, and another thing which I forgot to mention was that I had tried using my signal generator here to generate a higher pulse into the decoder. I got a little confused on how many RPMs I could handle with the 1 megahertz output from the Arduino for the clock line. Anyway, so I gave it even a 3 megahertz clock line here. No dice. The parameters for this test are 12 volts. I have a 5 amp current limit, which I wasn't hitting most of the time. Most of the time was pulling 2.5 to 3 amps. And it's going through that old speed controller that I had, which I made for the pendulum project, which has some problems. We're going to be working on that next. And the flywheel does seem to be quite a bit too large for this motor, but it's spinning it up, and nothing burned up or blew up or created any smoke, so I thought that was pretty encouraging. When I plotted the data, we did have a few good spikes in there, but I went ahead and just sorted those out manually. You can tell pretty much where they need to be since it's so linear. And then we have just the same graph with the spikes removed, nice and clean. And then I converted it to radians per second, and we plotted, and then the acceleration also. And then that green line is the torque, which suffers, its accuracy suffers from the major or even the minor spikes. But we have it in there. It comes out to about 0.25 Newton meters is the calculation that I have here. And these numbers are not guaranteed. This is my first draft. The flywheel's too big. The speed control isn't that great. But I just wanted to get some numbers out there, give it a test drive. 0.25 Newton meters for people in the US is about 0.2 foot-pounds. And just on a ballpark range, that seems about right. Just having held on to it, I don't know. It's kind of hard to say on these things, but it seemed pretty good. We got quite a few things to fix. We need to have the better speed control. I have my larger power supply. It's like 300 watts that we can use to drive this thing, bigger caps. Quite a few improvements to make. Work out this encoder issue. And I'd also like to do real-time plotting because I'm tired of copying and pasting on this thing. So we got quite a few things to do to make this better. And I'm looking forward to it. So thank you for watching.